Okay, in this video, I'm just going to work through the practice problems for the Unit 2 test. And here's the first problem. I ask a lot of questions. I promise you on the test, I might have a similar circuit, but I wouldn't ask you to find near as much information. But I just felt it would be good to be able to find almost anything you wanted to be able to find about this circuit. So I went ahead and I sketched out a picture here on a whiteboard. Get my whiteboard up. And the first thing that they asked us to find in part A was equivalent resistance. So we're going to have to do it kind of in pieces. I'm going to start with these two resistors right here. The 48 and 16 ohm resistor are clearly in parallel. If we think of a point from here to here, that's the same voltage drop across both of them. So 1 over the equivalent resistance, 1 over 48, plus 1 over 16, and that equivalent resistance at that point whoops, let me retype that, is 12 ohms. So a 48 ohm and a 16 ohm resistor in parallel is equivalent to 12 ohms. Now I'm only writing 2 digits, but in the original problem, when you look at it, everything had 3 significant digits. So our final answers will have 3. So this is going to be equivalent to 12 ohms. That means that that top row, you could think of the resistance as being 28 ohms plus 12 ohms is 40 ohms. The bottom row, if you look at these two, they're in series. They're not in parallel. They don't have the same voltage across them, but they do have the same exact current flowing through them. So our middle row has a resistance of 17 ohms plus 7 ohms, which of course is going to be 24 ohms. Again, if we look at the top row and the middle row, those two rows are in parallel. So if we want the equivalent resistance for the whole thing, it's going to be 1 over 40, that's the top row, plus 1 over 24. And this is actually the answer to part A. 1 over 40 plus 1 over 24. Take the inverse. And the equivalent resistance for the entire circuit is 15.0 ohms. I don't know if they're going to ask me for it, but I know that if the battery voltage is 60 volts, that the total current, I don't know if this, let's see, maybe this is question B, maybe not. Let's look and see. Yes, question B says, what is the current through the battery? If we look at that picture, our current through the battery is just going to be the battery voltage divided by that equivalent resistance for the entire circuit. So we've got a 60 volt battery. We've got 15 ohms equivalent resistance. So the entire circuit we think should be drawing 4 amps. So there's 4 amps of current that actually leave the battery. Hopefully so far so good. Next question. What is the current through each resistor? Question D says, what is the voltage across each resistor? C and D, sometimes it's easy to figure out current, and sometimes it's easier to figure out voltage. So let's just look, and we'll go C and D kind of back and forth. So I can easily get the current through the bottom row. If we labeled these, I believe this was R1, R2, R3, R4, and R5. So actually 4 and 5 are going to be really easy. To get the current through 4 and 5, and notice they have the same current. Looks like current's going to leave the battery this way. It's going to go up here. Some of it will go through this branch. Some of it will go through the upper branch. And then I'll come back down here. So for the middle branch, the current through the 4th resistor and the current through the 5th resistor will be the same. That is 60 volts from here to here, divided by 24 ohms in that branch. And we can see that the current that goes through that middle branch, 60 divided by 24, is 2.5 amps. So we do know that I4, which equals I5, is 2.50 amps. It's part of the answer to part C. The upper branch, we could actually get a couple of ways. We could use Kirchhoff's rule and say, you know, if there's 4 amps leaving the battery and 2.5 go this way, I think 1.5 better go this way. That's that junction rule. 4 amps going in, there has to be 4 amps going out. We just said 2.5 are going through this branch. I think 1.5 better go through the other. But let's do it differently. Let's do the upper branch current by just saying, hey, the upper branch, if we go all the way across this upper branch, is also 60 volts. The equivalent resistance of the entire top row is 40 ohms. And yes, that does come out to be 1.5 amps. So we know there's 1.5 amps going through the top row. All right, that tells me that I know what I1 is. So I've got the current through R4 and R5, and now I've got the current through this resistor, this 28 ohm resistor. All right, the problem now is this current's going to split. Some of that current will go through the 48 ohm resistor, some will go through the 16 ohm. We can look at that and think with common sense, more current will go through the 16 ohm resistor because it's got less resistance. But what we really need to know is, what's the voltage from here to here? What's the voltage across? Well, the easiest way to get that is to stop and say, you know what? What's the voltage across this? If I took a voltmeter and I hooked it up, here's a voltmeter, hooked one in here and one in here, what would it measure? The voltage across the first resistor is equal to the current that flows through it times its resistance. In this case, the current flowing through the first resistor, 1.50 amps. The first resistor is 28 ohms. So 1.5 times 28 is 42 volts. That's actually one of our answers because we're asked to find the voltage for each resistor. All right, so V1, I'm going to put that right here next to I1, is 42.0 volts. All right, let's think. We said from here to here is 60 volts. We can look, there it is, there's the battery. If this is 42 volts, then from here to here, if we do 60 volts minus 42 volts, that's going to be 18 volts. That tells me that V2, which is the same as V3, look, those second and third resistors, is 18 volts. They're in parallel, they have the same voltage. All right, that's going to help us determine how much current is going through. So the current through the second resistor is 18 volts divided by 48 ohms. 18 divided by 48 comes out to be 0.375 amps. That's I2. Tell you what, let me to get I3, we know it also has 18 volts across it, but only 16 ohms resistance. So it's going to be bigger. In fact, it should be 3 times bigger. And that comes out to be that I3 is 1.125 before we round it, or for significant digit sakes, I3 is 1.13 amps. Okay, so I've got all of my currents. I've got the current through the first resistor, the second, the third, the fourth, the fifth. If we add the second and third together, the 1.125 plus the 0.375, you can see that adds up to equal 1.5, which makes sense. The current through 2 and 3 should equal the current through 1. So far everything's making sense. We do want to go ahead and find the rest of our voltage drops. We can't see the picture, but we're not going to need it as much. We know we've got voltage through 1, 2, and 3. The voltage through the fourth is the current through the fourth times the magnitude of the fourth. The current through the fourth one was 2.5 amps. R4, I believe, was 17. It was 2.5 times 17 is 42.5 volts. The fifth resistor had the same 2.5 amps. They were in series with one another. It was only 7 ohms. That comes out to be 17.5 volts. Notice if you add those two together, you get 60 volts. That makes sense. So we have all, in red, we have all 5 of our voltages. In black, we have all 5 of our currents. And everything seems to fit together and make sense. If we go through, if we think about Kirchhoff, if we gain 60 and we take this bottom loop, we drop 42.5 volts here. We drop the other 17.5 and we're back to 0. If we take the upper loop, we gain 60, we go around. We dropped 42 volts across this first resistor, and then we dropped 18 volts as we're going to cross this parallel pair of resistors. All right, let's see what else that question asks us to find. We found current through the battery, current through each resistor, voltage across each, power used by each resistor. Power used by each resistor is just power is just VI. So if we want to do for the first resistor, it's V1, I1. The voltage across the first resistor was 42 volts. The current through the first resistor was 1.5 amps. 42 times 1.5 was 63.0 watts. We just continue that for each one of these. It had 18 volts. The current through the second one was the 0.375. Whoops, let me recap that. 18 times 0.375, getting 6.75 watts. The power in the third one, it too had the 18 volt drop, but I threw was the 1.125. I don't want to round in an intermediate answer. And that came out, it rounds to 20.3 watts. The voltage across the fourth one was 42.5. The current through the fourth one, that was the very first current we found up there, it was 2.5 amps. Comes out to be to 3 significant digits. I'm rounding all of these to 3. That's 106 watts. The power in the fifth one is 17.5 volts. It also had the 2.5. So 17.5 times 2.5 is 43.8. Now I did a bunch of rounding, but if we add all this up, let's see what we get. 63 plus 6.75 plus 20.3 plus 106 plus 43.8. It comes out to be 240 watts by the time I round it all to 3 significant digits. If we go back and look at the battery, its power, which is VI, is going to be 60 volts, 4 amps is 240 watts. So all of this makes sense. The power being supplied by the battery is 240 watts, and you can see how the various resistors are using that power, at what rates they're going through it. The last question says, how much energy does the battery provide if the circuit operates for 5 minutes? All right, energy is power times time. 240 watts. Remember, a watt is a joule per second. That means I need my time in seconds. 5 minutes is going to be 300 seconds. So I need to change this to 300 seconds. 240 times 300 is 72,000 joules. Or if we want significant digits, we could say, look, that's 772.0. There's my 3 significant digits, kilojoules. Or if you want significant, you could also say 7.20 times 10 to the 4th joules. A couple of different ways to write it that show 3 significant digits in your answer. All right, I think we've done a pretty thorough everything we could do with that circuit. Hopefully you will get where you can feel like if you walk through, all the voltage drops make sense, all the currents make sense. Let's move on to this circuit. This one really is going to require us to use Kirchhoff's. And one of the tips that we're going to need to use Kirchhoff's is the fact that we have a situation where we have 1, 2, 3 different EMF devices. See if it will let me. I think I can probably draw just directly on this one. Possibly, if my pen will let me. Here's a blue pen. All right, consider the circuit above. The current leaving E1, the first EMF device, is 4 amps, and you can see it right here. It's going this way. And it's traveling clockwise, so it's going that direction. The current leaving E2 is 4 amps and is traveling counterclockwise. So over here we have E2. Here they've drawn the current. Right there, it's going this way. Okay, this pen is a little different when I write on the Word document. What is current through the 5 ohm resistor? Well, look at this junction. We have 4 amps coming in. We have another 4 amps coming in. The only possibility is going to be that it all goes down this way. Has to be 8 amps. And you can see it. It will be going down this way, which makes sense. That was using what we call the junction rule. All right, what is the value of E1? If I'm going to find a missing EMF, I'm going to have to use the loop rule. So I'm going to start and get my pen a different color. No, I think I'll do is I'll highlight. I'm going to start right here, and I'm just going to go all the way around in that circle. See how that circle goes clockwise all the way around like this. But I'm going to start right here and draw right there. But why did that take off my highlighter going around like this? That is strange. There it is. All right, so let's get a different color. So I'm going to say, I'm going to start with E1. And then I'm going to have a voltage drop. I'm going to have voltage drop, remember, is I times R, so 4 amps times 4 ohms. And then I'm going to come down and I'm going to have a voltage drop through the 5 ohm resistor. But remember, the 5 ohm resistor has 8 amps times 5 ohms. Then I'm going to go through E3. Oh my goodness, I don't know E3. Guys, I didn't pick the right way to solve this problem. So let's erase and let's go back and draw a different loop, because that's what you have to do when you use Kirchhoff's rules. If you don't draw a convenient working loop, then you have to go back and change things. So let's erase. Let's erase this highlighter. Let's erase this. We still want to use E1, but let's make the big loop. I need to make the big loop because I know what this EMF device is. I have fewer unknowns. So I'm going to take my highlighter. I'm still going to start here. You know what I'm trying to think. I think I'd rather find E3 first. And I have a typo. This should say E3. I'm going to have to fix this. This should say E3. So let's start, and that may have been what threw me. Let's find E3 first. So let's start right here, and we're going to go around this way. So I'm going to start right at that point. So I'm going to go through E3, which I don't know, from negative to positive. I'm going counterclockwise. Then I'm going to have a drop. I'm going to go through this 6 ohm resistor with 4 amps of current. So 4 times 6. Then I go through the battery. Notice I'm going from negative up. When batteries, we normally go from negative to positive, so that's the correct way, plus 20. Then I'm going to go through the 5 ohm resistor. It's going to have 8 amps of current, so 8 times 5. And that gets me all the way back to where I started, all the way around the loop. So go in that loop one more time. I started right here. I went up E3, down 6 times 4 amps. I went up 20, and then I went down 5 times 8 amps. So E3, that's minus 24 plus 20 minus 40 equals 0. E3, that's going to be minus 64 plus 20 minus 44 equals 0. And that is the correct answer. E3 is 44 volts. Okay, and it says E2 here, but I know that we already know E2 is 20 volts. That has to be E3. I'll try to fix that when I get finished this video. So now we need the value of E1. Okay, now if I want to do that loop on the left, I know what E3 is. My other choice is to do the big loop. I kind of like the loop on the left, and I'll show you why. Because the currents will be correct. I won't have to go against the current. If this went this way, the current was always correct. If I erase this right here, now I can take my highlighter, start here, go around this way. Notice the current goes this way and then the current goes down. If my loop goes with the current, I don't have to worry as much about signs. When my loop is always going with my current, then I know that batteries are gains and resistors are drops. Anytime my loop goes against the current, then my batteries will be drops and my resistors will be gains. If my loop is going in the opposite direction as the current, which basically means instead of going where you're losing potential through resistors, you're gaining through resistors. All right, so let's do this one. We're going to go E1, and then we have minus 4 amps through 4 ohms. There's IR, 4 amps, 4 ohms. And then we're going to go down through the center, so minus 8 amps through 5 ohms. Don't you know what that is? And then plus E3. And then finally, we've got minus, we're going to have 4 amps through 4 ohms again. Maybe I can just drag that box out of the way. I don't know what it's doing. So E1 minus, whoops, it's minus 16 minus 40 plus 44 minus 16 equals 0. I need to solve that. When I do, let's see, negative 16, negative 40, wait, plus 44, minus 16, I get 28. E1 is 28 volts, and I do know that it is the correct answer. So practice making those loops. I want to do one more loop. I do not know how to make this editing thing go away. Let's do the big loop, and that's the one where we're going to have to really pay attention. So let's erase this green highlight, and let's look at what happens if I start here and I go all the way around this way. Okay, that's a little different. I want some room to work, so what I'm going to do, I'm going to do a little erasing. Since this is on video, the erasing shouldn't bother you. Now let's do that big loop. And I'm going to start right where I put that little crossbar. I'm going to go up E1. Well, we decided that the value of E1 was 28 volts. So I'm going to go up 28. I'm going to go minus 4 amps times 4 ohms. That's IR. I'm going to keep going. But notice when I go across here, all of a sudden I'm going opposite the current. That means I'm going from high to low in this battery. So instead of going up 20, I actually am going to go down 20. Then when I go through the resistor, instead of going down 6 times 4, I'm actually going to go up 4 amps times 6 ohms. I'm going to keep going around, all the way around. When I get to this one, now I'm going with the current again because this loop goes this way. So that's going to be a drop of 4 times 4. All of this is supposed to equal 0. 28 minus 16 minus 20 plus 24 minus 16. Let's check it out. 28 plus 24. Those are the two positives. That's 52. 16 and 20 and 16. That's minus 52. Definitely worked. But notice, when we're over here, the battery gained and the 2 resistors lost because the current in this part is going like this. But when we were over here, the battery was a drop and the resistor was a gain because the current here is actually going like this. And we were going the opposite direction. But all of that problem checks out. Okay, I'm going to stop our video here just because it's kind of a lot for one sitting. And I'll do the solutions to problems 3 and 4 in another video.